Okay, so welcome everybody to this new DaSCI seminar. Today's speaker is Professor Isabel Valera, who is going to talk about causethical machine learning from theory to practice. She is full professor of machine learning at the Department of Computer Science at Saarland University in Germany, and adjunct faculty at the Max Planck Institute for Software Systems in Saarbrücken. She is the recipient of an ERC starting grant on society-aware machine learning and a fellow of ELIS. Previously, she was an independent group leader at the Max Planck Institute for Intelligent Systems in Tübingen, Germany. She received her PhD in 2014 and her Master of Science in 2012 from the University Carlos III de Madrid, and worked as a postdoctoral researcher in Germany and at the University of Cambridge, UK. Her research focuses on the development of trustworthy machine learning methods that can be used in the real world, covering a wide range of machine learning approaches, from deep learning and probabilistic modeling to causal inference and time series analysis, among many others. I want to thank again Professor Valera for very kindly accepting our invitation. And whenever you're ready, the floor is all yours.
Thanks, Pablo, and welcome everybody to this talk. I really hope I can make up my mind around this. I was running for the last 45 minutes to make it on time because of a storm issue here. So today I'm gonna introduce what I call causethical machine learning, which is the intersection where we bring causal inference into machine learning in order to ensure some ethical or societal or legal properties from the algorithms that we develop. So whenever I talk about ethical machine learning, I mean properties like fairness, interpretability, even privacy or robustness. In particular, in my research, I focus mostly on explainability and fairness, as you are going to see later on. And I will show you why I believe that causality is a way of addressing these problems, and in particular, how to develop what I call causethical machine learning models, both from a theoretical but also from a practical point of view. So before I move on, let me kindly ask you that if at some point there is something unclear, please don't hesitate to stop me. I'm happy to take questions over the process. I'm not a big fan of these online meetings where I don't see many people or anything, so because I don't get any visual feedback on whether people are able to follow. So don't hesitate to raise your hand or directly unmute yourself and ask. I'm more than happy to be interrupted. So let me start, if I manage to move here, on why, first of all, we should consider what I call causethical machine learning. And let's start with an example that may relate to some people here, where we focus on algorithmic decision making. And basically, we take a bunch of features, in this particular case, education level and current job or current position. And the idea is that we train an algorithm for doing automatic filtering on a, for example, high-tech company, where here there is only 2 features for the sake of illustration, but just follow me on this, where we wanna see, we wanna automate a prediction on whether someone should be considered further for the position. And this is this probability of making a positive decision, which is moving further into the selection process, giving in this case a set of features, which I said education level, current position, but you can also consider other features. In addition, because as I said, we are focusing on ethical machine learning, we may consider or have ethical considerations related to fairness. And this is why I added here an additional feature, which doesn't need to be an input to our classifier here. But whenever we question about potential discrimination or potential biases of this algorithm making these predictions, we might need some this information. And now the question is, what is an ethical question about this algorithm? Basically, let's consider a case where We have Alice, who is a female with a master's degree and whose last employment was a heavy position at my university. So here a heavy position is an internship type of position for students here in Germany. So actually this is something I learned after I moved out of Spain. And it is that people have, students at the university can have employment within the university to fund their studies. That's very good for our students. I don't know whether this has changed in Spain. Definitely during my bachelor was not an option. And then she applied for a research position in a high-tech company and got automatically rejected. And you might have heard that many high-tech companies, they have algorithmic decision-making for pre-filtering applications, so she got directly rejected. So whenever we have such an algorithm, some consideration or ethical considerations that we have seen already in the news and in research papers is whether an algorithm may discriminate based on gender, whether, for example, it is disregarding or female applicants or having a very low rate of female applicants to be considered for the next step. And in terms of explainability, Alice may wonder in particular what to change in her CV in order to be accepted next time she applies, or at least being considered further, right? So these are two valid questions that a decision subject may wonder, because if we are in a case of discrimination, one may go to court, or one might go to civil organizations and plead. And in the case of explainability, it can be for two reasons. It can be for the first one as well in terms of fairness, but it can be also for Alice to understand how she could make it, because this is her desired position. So the question is, how do we answer these questions given that we have this machine learning algorithm and a set of features? And what I'm going to argue during this talk is that in contrast to our standard prediction models in machine learning, having just data in the form of features and labels might not be enough to answer these questions, because education and job might be input to the classifier, but for example, gender is not. So how can we even relate gender to education and job and to the output of that prediction system? And similarly, how Alice may want to change her set of features may have an impact. For example, the education level may have an impact on her last position, job, right? And that both of them can have an impact on the final decision. So in that sense, what I would argue is that many of these questions that we see in the literature of fairness and explainability today, but in terms of robustness, if you are interested, I can give you some pointers, actually can be seen as causal inference problems. And what do I mean by that? So I'm gonna map, first of all, this question of whether the algorithm discriminates based on gender into what we call a population level cause effect query or causal query, where basically we are gonna be interested in assessing how the distribution of the outcome, the prediction, will change for every individual if they would have all been male. So here what we are doing is that we are comparing a hypothetical world where all the population is a male population with a hypothetical world where all the population has been shifted to female. Of course, these two are hypothetical worlds that we cannot change in reality. But basically what we want to show or what we want to measure is how the gender information may have an impact in the distribution of education, which at the same time have an impact on the job, because very often you can only access a job depending on your degree or your level of studies, right? So for example, I can only be a professor at German university if I have a PhD, and I can only have a PhD if I have a master's degree, etc., but that it's applicable to other jobs as well. And what we want to see is whether our prediction system is basically incorporating in our set of features some sort of implicit biases with regards to gender that are being propagated to our decisions. That is what we want to look at. And in order to study that, what we want to see is how the distribution of our positive decision look like for all individuals, given that they would have all been males. So in this particular case, just for full disclosure, basically these two here is enforcing that independently of the person I have observed, I could simulate how this person would look like if had she or he be a male. And this one models how an individual person would have looked like had she or he been a female. So for females, we wouldn't be changing gender, but for males, we will be changing gender and then propagate what is the effect on their education level and job for that particular individual. That's a bit of a hard thing to measure at the first time, right? But let me give you an example because we very often see that. Let's imagine that gender would have been like a treatment, and this is how your blood pressure and your disease look, or not your disease, your symptoms look like, and this is the predictor of a disease, right? So very often what people have is a model on how the treatment may affect other features. So here our assumptions we are making is that when you get born as a gender, there might be some bias or some influence in how the education level distribution given a gender may be, and also how, given the education level and the gender, the access to different jobs might be. And as I'm gonna show you later, causal models allows us to do that not only at the population level, but also at the individual level, where we can assume that we have an individual, we can see what is kind of, you can think of the nature of that individual and reason how this individual, this person would have looked like given a different gender. And I know it's a very abstract point of view at this point, but I will give you a few more details later on. This is kind of a step one in causality. Just to give you another example, let's answer the second question that maybe might be a bit more concrete, such that you also understand these equations above, which is what can Alice do in order to be accepted next time? So let's imagine that now Alice, who is the person that we had here, right, now considers that instead of having a master's degree, she would have already studied a PhD, right? So in that particular case, we will need to see how Alice would look like with a PhD, but also keeping in mind that with high likelihood, the distribution of her job would have changed while doing the PhD, because she wouldn't be an intern, but she would be a PhD student under a scholarship or under an employment job as a PhD student, right? So when we assume that we would have, she wants to understand whether it is worth studying a PhD, we also need to account for the downstream effects of studying a PhD on the job, which is likely not to be an intern in a lab, but have a more like a full-time position, and how this intervention here in the education will have a downstream effect on the job and ultimately potentially change the prediction. That's what I'm trying to measure, right? And now the question is, how do I actually compute these quantities that I say here, right? And this is actually the goal of causal inference, where I have already told you that having data is not enough, because the first thing I have added from this slide to this slide have been arrows between my features. So I cannot assume that my features that input into the predictor are independent of each other, because it is unrealistic to assume that my education level doesn't affect my previous job, and that my gender may not have had an impact on how I have grown up, and also my education level, my interest, and my whole life development, right? So the question is that we are gonna question now is, what is the amount of information that we need in the form of, for example, these arrows, but also in the form of data, such that I can answer these questions in the form of these kind of equations and compute these equations with some theoretical guarantees. So you remember I started the title of my talk saying from theory to practice. So when we start from the theory part, I'm gonna say, okay, what are the minimum requirements that I need in order to be able to reason in a causal way, but also in a realistic way? Because I cannot definitely not collect what it is called interventional data, where I have a population where I exchange gender of people. That's not realistic or feasible. But under which assumptions from data about the world as it is today, I can reason about how my world would have looked like changing the gender of people. What are the necessary requirements or the knowledge about the world that I need to be able to compute these quantities? Okay, it's a very hard starting point, especially if you are not familiar with the causal inference. And just to dive in a bit into a causal model or into causal inference, let me simply tell you that a causal model is no more than a model about making assumptions about the data generation process, right? So given data, I can simulate the data generation process, and I'm assuming that my joint follows a particular factorization, which is given by my causal graph represented here. But what I said is that in order to answer my previous questions, I need to simulate how this data generation process will change when I perform an intervention, which is what I indicated with this do operator, where I enforce the education, for example, to be a PhD, or the population to be just a male population. So what does it mean in my case? Is that basically I want to also have a cost effect estimation at the population level. So I want to see, for example, how my gender and my job distribution would look like given that I enforce everybody to have a master's degree. Simply because of this causal factorization, I'm going to assume that the gender will not be affected by this intervention, but the job will be affected by this intervention. So that would be simulating a world where everybody has a master's degree. And then there is what it is called in causal wording or in causal inference, the cause effect at the individual level. People may have heard of the word counterfactual. That is what I mean here, where basically you might want to say, okay, given I have a particular sample of my population, I call it Alice before, how would Alice look like had she had a PhD? Right? And in particular case, given my causal graph, that would be, I assume that Alice goes here to my gender, and I perform an intervention where I enforce that Alice has a PhD, and I measure what is the effect of having a PhD in particular for Alice. That's what I'm measuring here, right? So these are the three quantities in simply in a different representation that I aim to compute using causal inference. So now, what the question is, okay, I want to be able to generate samples from the joint or to get an approximation to the joint under several assumptions of how my joint factorizes, but I want to also reason about what would have happened in hypothetical worlds where I perform or manipulate the system, right? Another question is, what do we need theoretically in order to be able to compute these estimates in a statistical way, which is equivalent to compute the three cause effects levels that I was mentioning in the previous slide. And that jumped very quickly. And the first answer that I have for you is that, as you may have seen already in the previous slide, is that data alone is not enough. Because the first thing I had to incorporate was these arrows, which is called the causal graph between my features. And now I have moved simply from gender, education, and job, right? To a 4 variable graph in the general case. So that I already added in the previous slide, but that might not be enough. So the theory of causal inference based on PER, actually mostly on Judea PER, this professor from UCLA, he introduced together with other people what it is called structural causal models, which is no more than a family of generative models where you make explicit assumptions about the data generation process. And these explicit assumptions usually come in the form of the causal graph, which is no more how our joint will factorize in a causal way. So you assume that somehow you can think in a temporal way that my education have an impact in my job, but not in the other way around. There might be cycles, but for the time being, we are going to assume that as at a given snapshot in time, by the time I collected my data, I got a sample and there is no cycle. So I have a DAG in my causal graph. So there are no instantaneous cycles, but a structural causal model also contains what they are called structural equations that basically say how each of my observed variables are generated from their causal parents, so X4 from X3, right? And an additional noise variable, which is often called exogenous variable. So basically here, X1 is a root node, and it will be just a transformation of a exogenous variable U1. And then X2 will be a function of X1, as you can see here, and another noise or exogenous variable U2. In causal inference, basically, the U's are simply representing, we usually assume causal factorization or the absence of hidden confounders, which assume that these U1, U2, U3, U4 are independent of each other. So they factorize the joint between P of U1, 2, and 3, and 4 factorizes. And basically what we are saying is that we can decouple every dimension from the exogenous variable, and what we observe is affected by this exogenous variable plus the parents. You can consider that, for example, if that would be the clothing I'm wearing, and this would be the temperature, right? There are many ways in which you can represent the temperature, or you can measure the temperature. But here, this is kind of representing the climate. This is how the climate goes into temperature. And this is how myself, I take this temperature and decide which clothing I should use. More or less. It's a kind of a hard thing to say. And these structural causal models are models about the data generation process. So what we assume is that what we call observational data are simply samples, IID samples, that are produced from a model of this form. And these observational data are what we usually use to train a classifier, for example, right? Where you simply get samples of features and maybe labels.
Isabel,
yes.
Can I make a question?
Of course.
So when you observe this data, like the observational data that you mentioned, do you have to learn or to infer the causal graph on the left, or it's some knowledge that you have beforehand in your context?
So I'm gonna focus on the causal graph to be given, as you will see. So very often causal reasoning is divided into two chunks. Causal discovery, which is given the data, how do I go to the graph? And then there is causal inference, which is given the data and some additional information, for example, the graph. How can I answer queries of the form that I like of the estimates that I put on the previous equation?
Okay.
As for today's talk, I'm going to assume that the causal graph is given due to domain expertise, right? So domain knowledge that can tell us what comes first, or that you can run some causal discovery tool to get the graph. And I'm going to
Okay.
focus on causal inference. But that's a very
Okay.
good question.
Okay, thank you, thank you.
My pleasure. So an SCM has one property, which is a generative model from which we can get observation and samples. But it has another property, which is it allows us to simulate interventions in the form of a do operator. What we do when we intervene on a random variable or in an observed variable is that we break any incoming edges to that variable and we can fix a value. So now here we have an alternative data generation process where we have changed the mechanics or the dynamics of the system by making that now our x2 variable takes value alpha deterministically. So you can think that x2 is now a delta function in alpha, p of x2. So what this do operator allows us is to, as I said before, is to see how my world in the form of this data generation process would change if I would, for example, break down the causal dependencies of x2 with respect to x1 and fix a particular value. Something that it is important here is that in order to reason about the cause effect of actions, first thing I need is a model that allows me to perform these two operations and simulate what would things look like. But something that it is even more important is that if I want to see the effect of an intervention of this form at the individual level, which, as I said, is what we usually call a counterfactual, then you need to fix the values of the use for that subject, such that when I perform alpha 3, I can simulate how the resulting F3 would look like when I replace X2 by alpha here, but for the same value of U3. So just to be very to the point here, the main difference between interventional and counterfactual data is that in interventional data, I basically consider the whole distribution of the PU1, PU3, and PU4 in order to generate new data samples. While in counterfactual data, what I say is that for every sample that I got from the observational data, I would, which is called factual, I would like to know how X3 and X4 in this particular case, which are the only ones affected by an intervention in alpha, would look like for that particular individual if X2 would have taken value alpha. And for that, I need the actual value of these exogenous variables. So the problem of performing inference on U1, U2, U3, and U4, such that we can compute counterfactuals, is usually called inference in this setting. And usually there are theoretical results that tell us under which assumptions we can identify at the individual level this use. Why am I saying this? Because any generative model can run or get samples from the joint distribution. You can factorize this in many ways, but as soon as you want to see how an intervention in X2 will propagate to X3 and X4, you need at least assumptions on the causal graph if you want to look at the whole population level. But if you want to do that at the individual level and you would like to see how Alice will look like once she gets a PhD, then you need to be able to infer the actual value of U1, U2, and U3, and U4 for Alice, such that they can propagate the effect of alpha in these two equations. Okay, so I hope that was more or less clear. I hope so. So basically, now what I just said is that actually SCMs, or these structural causal models, allow us to perform causal inference to estimate cause effects. But the problem is that I have made a lot of assumptions in order for applying them. What are these assumptions? Basically, that I have the causal graph, that I have the structural equations, which means I know which parametric forms there are from F1, F2, F3, and what are their parameters. Also, it's not explicitly written, but usually I need to make an assumption on the distribution of the exogenous variables, and I need observational data such that I can perform interventions and measure intervention and counterfactual data for estimating the expectations I had in my previous slides. And that, unfortunately, are way a lot of assumptions that go much more beyond the standard assumptions that we consider in the machine learning pipeline for prediction. So a lot of work or a lot of criticism for the causal inference side, not only in the context of ethical machine learning, but in general for causal inference, where there are many problems that can be phrased in a causal way, is that, okay, you have a lovely theory that tells me I can do that, but the assumptions I need to make about the world are so difficult to fulfill that there doesn't seem to be any practical use of these questions. Well, moving forward to the second part of the title of my talk, I said, okay, this is what, in theory, we know that if we have all this information, then I can answer all the questions about fairness and explainability I gave you at the beginning of the talk. But now the question is, that doesn't sound practice. So how do we move from theory to practice? And this is where I'm gonna enter now. So what are the minimal and to the extent possible realistic assumptions I need to make in order for causal inference and ultimately, in my case, for causethical machine learning? So in that case,
Sorry,
I'm not gonna...
sorry, Isabel.
Yeah.
Sorry for the interruption. I think,
No worries.
if I'm not mistaken, I think Mohammed Hisham Ismail has a question.
Yeah, I
because
didn't
he-
see. It's simply that if I put the participant list, I don't see the slides.
No worries. Yeah, no worries, because I can tell you if
Perfect.
somebody is
Happy to
asking
take a
something,
question.
and I will say that Mohammed has raised his hand. I don't know if you want to ask directly, Mohammed.
Hello, Doctor. Thank you for the insightful presentation. I just have one question regarding the assumptions. Does structural causal models typically assume a Markov property?
Yes. So I am assuming that the causal graph is a DAG, and therefore they need to factorize in the way I wrote here, right? Which is equivalent to say that my structural equations only depend on the exogenous and their parents, and that the exogenous variables in this case are independent from each other.
Okay, thank you, Doctor.
So now the question where I want to move is, okay, can I do something under more practical assumptions that are assuming that I actually know the causal graph, which is a bit more constrained, all the structural equations, which is basically saying how my exact data generation process should be? And the answer is that yes. So in general, I showed, or theoretically, we are able to solve that under certain assumptions on the data generation process. I'm able to generate observational, interventional, and counterfactual data with only the causal graph, for which, by the way, I will explain later, we may have only partial knowledge, and observational data. And under some assumptions, which are usually work quite in practice, I'm able to generate the three ranks, as they are calling causal inference, which is observational, interventional, and counterfactual. How do I propose to do that? Basically, with a family of generative models, which I call causal generative models. Usually they are going to be based on deep neural networks, but basically what I need to define is a generative model of the form that we are used in the machine learning community, a generative model which is probabilistic, so not the LLM type transformer like, but more like in the family of VAE, normalizing flow diffusion models. Okay, just for full disclosure, where basically I want these three capabilities, and in order to get any theoretical guarantees on the data that I generate at the observational data, then I need to perfectly fit my observed data accurately. That is a constraint that we have in any generative model to synthesize data. But in order to generate interventional data, basically we need to ensure causal consistency. That means that my causal graph is consistent so that the factorization I'm assuming is the one that really generated the data. And finally, in order to generate counterfactuals, as I explained in my previous slide, I need to be able to identify to some extent, at least the U variables. I will explain you later to which extent. So in that context, I have done quite a bit of work in this line, where basically for those familiar with the machine learning community, I have shown that one can generate both observational and interventional data using Gaussian processes and VAEs. We have also combined variation autoencoders with GNNs. And only last year, we managed to, for the first time, come up with enough theory on a deep generative model using normalizing flows, which allow us to generate also counterfactual data with theoretical properties. So I'm gonna basically focus on this last work, but if you are interested, you can also gossip a bit there. So how do we actually propose this causal normalizing flow with two of my PhD students? Basically, we need to make some assumptions on the model. So we are going to assume that we have a true data generation process of this form, where the structural equations, while unknown, we assume that they are invertible and differentiable. So these F functions, they need to be invertible and differentiable with respect to the U's, nothing else. That our causal graph don't contain feedback loop, so it is a DAG, and that our U variables factorize. So this is called causal sufficiency. And then under these assumptions, I actually can guarantee theoretically that we are able to fulfill the three requirements I explained before. So how is that the case? I'm gonna go one by one. First, because I basically show that autoregressive normalizing flows, which is basically a family of neural networks which are differentiable and autoregressive in the sense that their Jacobian is lower triangular. Basically, I can show that both structural causal models with the family of with the assumptions I established before, and autoregressive normalizing flows, they are all triangular monotonic increasing maps, which is no more than saying that they are functions which Jacobian is upper triangular with respect to the input. So, and because autoregressive normalizing flows are universal approximators of triangular monotonic increasing maps, and we can actually show that SEMs, as I was saying, are a subset of these triangular monotonic increasing maps. Basically, what I'm saying here is that an autoregressive normalizing flow, ANF, can perfectly approximate, is a universal approximator of any structural causal model with the properties with the assumptions I explained before: differentiability, invertibility, causal sufficiency, and a DAG as a causal graph. So that already guarantees that we can fit the observed data accurately, which is the basic main constraint for any causal generative model. But what about our interventional setting? We needed to be causally consistent. And here, maybe you don't need to go very much into the theory, because I have actually done a few math. But basically, if you have a structural causal model of this form, that induces this observational distribution, and we have a causal normalizing flow that induces that distribution, basically, I can show that as long as these two models induce the same observational distribution, so they can fit perfectly fine my data that I use to train, then both models are gonna be equivalent in the generation from U to X, both recursive or in vectorial form. As recursive simply means I go from U to X and from U and X to the next X. Generative, I mean in vectorial form, where I can do all the U's into one X that you can do for any autoregressive model, but also in the adaptive setting where I say, okay, I can make sure that the U's that I obtain from X, the posterior of P of U given X, only depends on the X's that it should depend according to our causal graph. So that is the second requirement that I had in order to be able to generate interventional data. And the last one, sorry, I forgot that here. This is a bit of a minor point I forgot I was mentioning here, is that this is warranted as long as these two exactly induce the same distribution. But of course, this is a deep neural network, so we may have some local optima. And I will show you in a few slides how we can guarantee that by design. But that is a kind of a minor detail I forgot I had not removed. So the third property in order to generate counterfactuals is that actually I need to be able from X to identify the exogenous variables U. And this is in the theory side, but I think it's much easier to see it graphically. So if I have a SCM here and I have a causal normalizing flow, which remember is just a neural network which is invertible and which Jacobian is a lower triangular Jacobian, then basically what I can tell is that if both of them induce the same observational distribution, which was my property one, then I can show that there is a one-to-one mapping between the distributions or the use of for both models, the endogenous variables, that basically are the same up to a component-wise transformation. So I might not be able to exactly recover the true U for every individual, but I can obtain the same one up to a component, so dimension by dimension transformation. And that is already enough for us to be able to generate counterfactuals with theoretical warranties. So these were a lot of details. I hope you managed to get at least the most important parts, but just as a recap, remember that in theory, what we have shown is that autoregressive normalizing flows with causal ordering is actually enough for performing causal inference, and we can learn any SCM with the assumptions I mentioned at the beginning. Of course, there is the question that in practice, neural networks love local optima, and we also need to implement in a neural network the dual operator, and we very often have limited real-world data, so it's exactly ensuring that both distributions are the same can only be done at the empirical level. So the question is that how do we do that? Well, we can basically design, and I'm not going to enter in details on that, but we can definitely design normalizing flows that are causally consistent by design, which will remove the problem of local optimum. And that will already ensure that all the errors that we do in our estimators will not be anything else than empirical estimates errors that we can further reduce when we observe more data. And for practice, I'm not going to enter in the details because that's very hard to explain in a 45-minute talk, but if you are interested in the paper, we show how we can perform interventions in a normalizing flow, and also how can we handle mixed data types. So we can handle categorical, numerical variables all together, as well as partial causal graph, where maybe some of the edges between the variables might not be clear due to the inconsistency in the causal discovery. So I'm going to skip that. So this is basically an illustration of what I said. These are for categorical data, and this is causal graphs. but I'm gonna basically simply show you that we did a lot of empirical evaluation in a lot of data generation processes, synthetic data generation processes, and we were able to compute how well we were approximating. The KL is in the observational level, the AT is the average treatment effect, which is the interventional level, and this is the root mean square error for the counterfactuals, because remember we assumed that we had the true data generation process, and we were able to approximate that with very small errors and definitely better than the state of the art. How did we basically use that? I closed the loop by saying, well, I was interested in fairness and explainable machine learning. So just as an example, we use it for auditing fairness of a classifier, and in particular counterfactual fairness, which is no more than the definition I gave you at the very beginning. And we basically are able, with our causal model, to train a classifier which is as accurate as an unfair classifier or even more, with a zero level of unfairness. So we were even able to demonstrate that this trade-off that people talk about, fairness and accuracy, doesn't need to even exist if we adopt a causal pipeline. And for the first time, we were able to do it in a practical way. And this is all on real-world data from, for those familiar with the fairness literature, this is the German credit data set from the UCI repository. And just for illustration, this is how the real data looks like in the observational and in the do operator when you have the dots. And our approximations of the distribution for one variable is the solid lines here, which are quite accurate. I mean, the errors are due to empirical errors. So I had more material because this is a bit of a long talk, but let me conclude by saying that basically deep generative models, actually, and in particular normalizing flows, causal normalizing flows, can be a good practical approach for causal inference in practice, which for the first time got theoretical warranties in the deep learning community for causal inference in a fully amortized way. And of course, there are a lot of assumptions that we have done, like there are no unmeasured confounders of the form that I show here, and that there is not a misspecification in the graph, which I hope I can address in my future work. But at least I hope we have moved one step forward into that direction. And just to finalize, simply remark that why am I doing all this causal inference? Of course, causal inference have a lot of applications, but in ethical settings, it becomes very relevant to be able to reason about changes in the world and systematic biases in the data generation processes, where you can actually not collect, or it is infeasible or unethical to collect interventional data. And in that case, basically, it is very important to see how far we can bridge theory and practice in this setting, and whether there is an approach that can bring some light into the fairness and the explainable and the ethical machine learning pipeline by using causal inference into practice. There is a bit more in this slide, but I think it's better if we move to the question side, and I'm happy to follow up if there is any particular aspect that needs to be covered. Thank you.
Well, Isabel, thank you very, very much for this very nice talk. And now is turn for the questions. Now, Mohammed, whenever you want, you can ask your question.
Hello again, Doctor. Is computational efficiency a challenge when designing interventions in SCMs?
Yeah. So in SCMs, in our degenerative model.
SCMs, especially when talking about interventions.
Yeah, no, so I mean, SCMs in structural causal models of that form, right? So I basically, let me go here, maybe. So here, right? So
Yep.
this is an SCM, which makes explicit assumptions about the structural model, right? And this is just a neural network that can approximate that one. So here, if you know these Fs, interventions are not costly at all because it's basically replacing these functions by a deterministic value, right? The problem is that usually you don't have that. In a normalizing flow, it's a bit more difficult because this is a neural network where you input U and outputs X, or in the other way around because it's an invertible neural network, right? So when I wanna do an intervention at this particular level, because a neural network works in the vectorial form, not in the autoregressive, it's a bit more puzzle. In our case, that only takes one forward pass and one backward pass. So it's basically duplicating inference time of a neural network, and that is quite efficient in general.
And in this case, can state space modeling, for example, simplify these computations, or it doesn't have any effect?
I think the problem of these models go when the dimensionality of X becomes very large. Basically because I'm gonna try to go here, right? So this is the Jacobian, which is the partial derivative with respect to the U to the X, or in the other way around. It depends on which direction you are looking, because remember it's invertible.
Yes.
So in general, the computation comes from the invertibility. The cost of the inverting this is where the computations come. And there are many autoregressive normalizing flows. So there are simpler ones which are very easy to compute, but then they are not as expressive. And there are others that are, for example, based on splines, where inverting or computing the Jacobian becomes, even if it is lower triangular, becomes expensive. So I think definitely in order to scale up to high input spaces, because here this needs to be invertible with the dimensionality of your observed data, right? Then is where the scalability problems come from, and where we probably would need to see what can be done. That is one of our future to-dos, indeed.
Okay, thank you, Doctor.
Okay, now we have another question from Pablo Morales, whenever you want.
Yeah, hello, Isabel. Thank you for the talk. It was very nice. I have actually had a question, but now I have another one related to this previous thing. So, in what order of magnitude do you have the number of variables that you are using? Because in the past, I have used these normalizing flows a bit with the real MVP, but going beyond tens of variables, I was having some problems. So I think it's related to what you were mentioning before, like around how many variables were you handling in your data sets?
I mean, in general, I was handling only a few tens, right? Okay. And that more or less can be done. So in our synthetic, where I show the time computation, which is here, right? It's still more efficient than, for example, GNN-based approaches. And we are talking here about training evaluation in the order of, this is in microseconds. So that was very efficient, but we are in the order of 5 to 20 samples. Features. As we grow, the computational complexity scale up depending on the autoregressive normalizing flow that you use, quadratically or cubically in the worst case. And there is when you start having problems, especially with training, because every evaluation of the log likelihood requires an inversion.
Yeah, I remember that either the forward or the backward parts, depending on the type of normalizing flow, it's costly.
So I think right now we have been running additional experiments because we have extensions for hidden confounders, and I believe we have gone through to 50 to almost 100 features, and that still is scalable, but I think over 100 we would need to consider a different type of architecture and see whether either we can find another architecture that falls into the triangular monotonic increasing maps, right? Or we need to revise our theory to relax further this assumption, for example, and be able to have an autoencoder type of architecture. Does it make any sense what I'm saying?
Yeah, no, absolutely. I was curious about it.
Yeah, it's a lot of questions because there is deep learning, there is causal inference and standard machine learning, and so it's a bit of too many things at the same time.
But very interesting to see it playing together. One more thing is, did you mention, so when you mentioned the case of, like, you want to do predictions for the case of Alice, and you call that counterfactual, if I remember correctly.
Yeah.
And you said that in that case, you have to estimate like the use for that particular instance. And did you mention or gave an intuition about how to obtain those use for a particular person or a particular instance?
So in our particular case, right, so if these functions are invertible and you would know these functions given x, you would need to solve the equation. And if they are not invertible, you end up getting a posterior of p of u given x, right? So that is the standard SCM approach. In our particular case, because we fall in the invertibility assumption on the true SCM and also on the normalizing flow, there is a one-to-one mapping between x and u. And there, once you have assumed that this is this result, right? Once you have assumed that these two match in observations, so they produce the same observations, then you know that the use that we are obtaining in our normalizing flow are just a element-wise transformation of the original ones, and you don't need to know the original ones, but you know that they basically contain the same information, and this transformation is the same across the whole population. So basically what we are saying is that these two models are causally equivalent. So they basically may have different functions, but they generate exactly the same distributions at the observational, interventional, and counterfactual levels. And for that, they need to generate the same use up to a point-wise transformation. Point-wise means dimension by dimension.
Yeah, okay. Yeah, but this H is are not necessarily invertible.
No. And they don't need to be known. I think in this case, maybe because we are assuming that the whole system is invertible, these H's might need to be again invertible, but they don't need to be known.
Okay.
But at the same time, it's like assuming that, I mean, the use usually are unmeasurable, right? So it's basically, you can think of, in our structural equations, it's easier to understand these use are capturing the entropy in X2 that cannot be explained by the parents, right? So it is how much of uncertainty there is in X2 given the parents, and this is fully captured by U2. And there are, as long as the use here and the use here share support, in our case, we are in the real numbers, right? And you don't put zero mass on a value of U that cannot be under the other one on the transformation, you shouldn't have any problem. So it doesn't really matter what is the underlying true distribution of the U. You know that somehow you are capturing kind of the uncertainty for every individual and for the whole population. And so if you would think in terms of entropy, that says that you can capture perfectly fine the entropy of what is not explained by the parents on any observation. I hope.
Great. Well, thank you very much for the talk. It was nice to learn some causality.
Yeah, I hope I hope so. Thank you.
Okay, I think we have time for last question or another question. Do you have more questions from the audience? No?
There was a lot of information to process, most likely.
Well, maybe, but I think we all have learned a lot. I have a question, in fact.
Yeah.
This is something you mentioned as future work, but can you tell us a bit about the metrics you use for causethical machine learning and the problems associated with existing metrics? I don't know if you can tell us more about this.
Yeah, so I can do. I have an example here for, let me see. Yeah, I have an example here for causal inference. Sorry, for fairness. So here, right, this is the German credit, the causal graph on the German credit, removing the label, which is whether someone repays or not. Only using 7 of the 8 of the features, where I assume that sex is the sensitive attribute, right? So one notion of fairness is called demographic parity or disparate impact, which makes sure that the distribution of or the rate the positive outcome should be kind of, or the prediction, the positive prediction should be invariant for everybody, right? So here what I'm doing is that I'm applying counterfactual fairness, which says that basically I want my distributions to be, my predictions to be invariant to the gender. And for that, I can simulate by saying that I want the probability of PD equal 1 for all individuals in my population, right? If they would have been males, to be the same probability that they would get for the positive outcome if they would have been a female. And what it actually does is that this turns out that we can make predictions based on the use or our estimations of use, removing the use of the sex, or even if you want the age, because as long as you have mapped your features to the U space, basically you know that the U of the credit amount or the U of the checking account of the saving is unbiased compared to the bias compared to sex. And that is why in the Kushner et al. Paper from 2017, they show that making predictions on you is counterfactually fair by definition, and actually doesn't need to end up in a drop in accuracy. This is what we show. And coming back to the demographic parity, one actually can show that this classifier is demographic parity fair, because basically you are making predictions. So you know that if you are counterfactually fair, you are demographic parity fair, but not in the other way around. So not all the solutions of them. Sorry, my dog is complaining. I guess he needs a bit of a walk. I don't know whether you hear him. He is complaining.
No, we cannot hear. Well, at least I'm not hearing anything.
That's good, because he's making like noise, like pay attention to me.
Okay.
And basically these are the kind of results that you can find. So basically you get a particular approximation or a particular practical solution for counterfactual fairness that guarantees that the predictions are independent on the sensitive information, and as a downstream you are demographic parity fair without compromising in accuracy. We have also used that for, I'm gonna show you here a bit, for actionable explanations. I call it algorithmic recourse, causal algorithmic recourse, which is how can I guarantee that what actions do I need to make in order to change my prediction? And also we have studied fairness in terms of the cost of recourse, but also we are now able to study with this kind of pipeline the cost of, let's imagine that this set, these are the people covariates, and this set is the loan terms, right? Now we can even measure what is the indirect and direct effect on these decisions. So assuming that the interest rate and the duration of my loan will not affect whether I'm able to repay is a very not fair, like not very realistic decision, but also assuming that there might be not bias from the bank on how they set this is also unrealistic. So now we can also measure the dash red and the solid red together and separate, which is how the sensitive information may have affected the loan terms, and also whether the disparity in the loan terms across demographic groups may have a downstream effect on the Y. So these are kind of the applications we are looking at. So looking for the different sources of unfairness, which ones are responsibility of the decision maker, which one are the responsibility of the society and maybe policymakers, and also looking at the final individual by giving them with more actionable explanations that they can revert an unfavorable situation. All this in the algorithmic decision making, but some of these ideas could even be extrapolated to the Gen AI pipeline in the image or in the language domain, although that I haven't yet fully scaled it up.
Okay. Well, thanks a lot
My pleasure.
for this answer in particular and for all the answers and your talk. So I don't know. I think we can end here this DaSCI seminar. I want to thank Professor Valera again for
You
accepting
can
our
call me
invitation.
Isabel, that's all good.
Well, Isabel.
Spanish style, we call by first name, I think.
Okay. And well, that's all. I think we'll see you on the next DaSCI seminar that will take place in 2 weeks.
Thank
So,
you all.
thank you, Isabel.
Gracias. I owe you a visit to Granada, I guess.
Whenever you want, we will be more than happy.
Okay, thank you, bye.
Bye-bye.